I'm Shivaram Venkataraman, and I'm presenting this work that was led by Pengfei Zheng, Ray Pan, and Tarannum Khan, and in collaboration with Professor Aditya Akella. The authors were at the University of Wisconsin and UT Austin while we did this work. Today I'm going to talk to you about fair and efficient GPU sharing for deep learning workloads under this new regime that we call as dynamic adaptation. So the setting for this talk is this idea that enterprises are creating large clusters which are shared across many users inside the enterprise, with the goal being that users can submit their machine learning training jobs to be executed on this shared cluster. In such a context where we have shared clusters to do, which are shared among a large number of users, an important part of the puzzle is how do we kind of multiplex access to the shared cluster between all of these contending applications. So this is where there's this new box in the middle that we insert called as the cluster scheduler, whose role it is to receive these applications that are submitted by data scientists and then select which of these applications could get which resources on this shared GPU cluster. Now, along with the changes and evolutions in machine learning workloads, there are some new challenges that are being introduced in designing these cluster schedulers. One such phenomenon that formed the motivation for our work is this notion of dynamic adaptation, which refers to the fact that machine learning training jobs could change how they use the resources during the lifetime of the job. So I'll give you a couple of examples of how this happens in practice. So one arises from this idea called gradient noise scaling, which relates to how the batch size that is used by this job can actually be adaptively changed during execution. Specifically, the batch size can be doubled based on the gradient noise that is observed during training. So if one way that the system might look like is that the job might start with a small batch size, let's say 16 at the beginning, and the user might configure a large batch size or an upper bound as, let's say, 4096. And during the job's execution, the batch size is adaptively doubled from 16 to 32 to 64 and so on. As you can see from the right side figure here, these events might be triggered at various different points based on how the training is progressing for this specific job. There's some systems like Kung Fu and NSDI 2020, which actually provided system support for executing such dynamic adaptation. There's not just one such pattern. There's been more research in terms of other ways that you could actually adjust the batch size during training. Prior work in my group has developed this work called accordion, where we found that you could use a small batch size in critical regimes of training, which is typically when the learning rate changes or during the initial few epochs, and then you could use large batch sizes everywhere else. Again, we look at the gradient information to figure out when is it a critical regime versus when is it not a critical regime. So overall, this trend that jobs might actually change how they behave during execution introduces a lot of new challenges in both efficiency and fairness. So taking a look at efficiency, so let's say I have a job 1 here which arrives with a batch size of 16, and based on that, I estimate that its runtime will be 8 seconds, as shown in this example. But let's say after 2 seconds, the job changes its batch size and now uses a much larger batch size. This typically accelerates training, and the job might finish in 4 seconds. So given that you have a collection of such jobs that arrive at the scheduler, if we, for example, are agnostic to this behavior that there might be changes in jobs resource use, we might end up with a resource use pattern that looks something like this, where job 3 is scheduled only after job 2 finishes, extending the overall execution time to around 10 seconds for this small example. Now, of course, the scheduler can react to these batch size changes. So as soon as it observes that job 1 and job 2's resource requirements have changed, we can kind of prioritize job 3. So we call this as reactive scheduling. And in this case, you can see that reactive scheduling helps, but you still end up with a scenario where the overall makespan of this little trace ends up being 9 seconds. Now, the best case scenario for this particular example is if we are somehow able to predict that these adaptations would happen, and then we could do proactive scheduling, where we allocate job 3, which is not going to change in the future, to run on one GPU while we share the other GPU between jobs 1 and 2. And you can see that this leads to a lower bound of 7 seconds for this small example. Not being aware of dynamic adaptation also could affect fairness in large clusters. So here we look at how Themis, which was our prior work on doing fair scheduling for deep learning clusters, and inside the working of Themis, Themis tries to estimate what is a fair job completion time for this particular job that's running. And you can see that if the epoch durations go down over time, the estimate that Themis makes is off at the beginning, because at the beginning, it doesn't really know that there's going to be these changes that are happening in the future. And our experiments show that this can lead to almost 2x worse finish time than a fair finish time for this particular job. So the central question here from all of these trends is, how can we sort of achieve efficiency and long-term fairness when you have this dynamism that's present in machine learning workloads? So to address this, we propose a new system called Shockwave, which is a fair and efficient scheduler for workloads under dynamic adaptation. The key contributions in Shockwave are we use a predictive model that tries to estimate or predict dynamic adaptation in machine learning workloads. And then we plug that into a market-based formulation, which gives us actually some provable guarantees on efficiency and fairness. We show that this can improve makespan and fairness by 1.3 times and 2x compared to state-of-the-art schedulers using a number of different workloads and scenarios. So next, I'm going to switch gears and talk a little bit about more in-depth issue of what are the challenges that come up. And then I'll give a brief overview of Shockwave's design and summarize our evaluation results. So there's been a lot of prior work in deep learning schedulers, and this started with many different policies that were proposed to improve cluster utilization, starting from Gandiva in 2018. And many other works have also focused on reducing job completion time and also optimizing good put or sort of how much accuracy jobs achieve by using this notion of elasticity, including works like Slack, Optimus, and Pollux. The work sort of closest related to our work here are these works which try to do fair sharing across different users, like Themis, Gandiva Fair, AlloX, and so on. And so I'll use those as an example to highlight what are the new challenges introduced by this dynamic adaptation. So let's first take a look at how do existing fair sharing schedulers try to achieve this notion of fairness by adjusting the allocations over time. So typically, these schedulers track some notion of what share of the cluster resources have been allocated to this particular job in the past. And based on that, they try to estimate what will be the finish time and then try to judge whether you should increase or decrease the allocation based on that. Now, clearly, you can see that whenever we try to estimate the finish time, existing schedulers assume that jobs will behave as they have been behaving in the past. And if there are changes in these batch sizes that are going to happen in the future, you can get wildly inaccurate estimates. So this means that this notion of what would be the finish time under fair allocation, these estimates are often very wrong, affecting the overall schedule that the schedulers are able to come up with. The second challenge is that once you have these estimates of the fair finish times, existing schedulers also only look at the past allocations to kind of adjust the allocations for this current round of scheduling. So typically, scheduling proceeds in multiple different rounds. Say a round duration is 2 minutes or 5 minutes. And if a scheduler like Themis gets these finish time estimates for all of the applications, it can then look at what are the applications which have the worst finish time fairness so far, or the highest values of rho, as I'm showing in this figure, and then prioritize allocation to those subset of applications. But now the catch here is that the values of this filtering-based approach, it only looks at sort of the past allocations and does not have any ways to account for how these allocations are going to look like in the future. So to address these two challenges, we sort of designed this new approach where we use this prediction-based model that can capture long-term efficiency and fairness. And we also use a mechanism, which is market-based design, which can actually perform allocations for future rounds and sort of see what is their effect on this long-term efficiency and fairness. So there are two key design components in this. One is a Bayesian modeling-based approach that can predict this utility under dynamic adaptation. And the second is this market-based solver that can give us provable guarantees. And I'll talk about both of these in a little bit more detail now. So let me start with this Bayesian-based model. So our challenge here is that we would like to predict the utility of future epochs in the presence of dynamic adaptation, which is often triggered by the user jobs and not something that the scheduler can control. So the key insight that we use in order to approach this challenge is that we observe that there's a handful of patterns that jobs use. It's not necessarily just GNS or just accordion, but a handful of such patterns. And these handful of patterns typically have this notion that you use a particular fixed batch size for a range of epochs. So one way we can kind of model this is that we can model this as a mixture of different regimes, and each regime has a specific fixed batch size. So in this example that I'm showing you here, 0 to 10 epochs has a fixed batch size, let's say 16. 10 to 20 has a fixed batch size of 32. 20 to 30 has 60, 20 to 40 has 64, and so on and so forth. So now that we have these fixed regimes, we can use standard profiling approaches to get the performance of each of these regimes. And what our modeling needs to do is just figure out what fraction of the epochs are going to be in which regime. So this is where our Bayesian modeling approach comes in, which is that we use this mixture of regimes as a Bayesian-based model, where let's say there's a job which runs for 100 epochs, and the ground truth is that it has 30 epochs with small batch size and 70 epochs with a larger batch size. We start off with a prior estimation, right? And our prior might say that there's 50 epochs with small batch size and 50 epochs with large batch size. So we model the mixture using this prior, or we initialize the model. And we observe these batch size scaling events that are happening during runtime when the job executes. And based on the observations that we have, we update the posterior of this distribution. So based on the scaling events that we observe, we might update our distribution to say that now it's 65 epochs are in batch size Y12 and 35 are in batch size 4096. So as you can imagine, with this kind of approach, our estimates just keep getting more and more accurate over time. And time here can be modeled as epoch progress. And here we can see that this Bayesian-based approach actually has much lower sort of runtime interpolation error when compared to a greedy approach for assigning these mixtures. In the paper, we also discuss an improvement to the Bayesian model where we can actually come up with a new way to do this update of the posterior, where we describe a new restatement rule that only updates the parameters for sort of the completed epochs, and more details of that are in the paper. So this completed the first part, which is that given a sequence of jobs that are executing, we're able to kind of predict what is their mixture of regimes going to be, and thereby what is their overall expected runtime going to be in the future. Now, given that we have these predicted runtimes, we switch to discuss how we can actually use those predicted runtimes to come up with an allocation that takes into account and achieves long-term efficiency and fairness. So we specifically use economic market theory, which helps us sort of get these provable guarantees for efficiency and fairness. And we model every round of allocation as a market in this case. Now, economic markets have been used in a number of different schedulers in the past. And typically, the way these are modeled is that every job has some budget, and you define a utility function saying that if you achieve this allocation, you get some utility as a result of it. Utility here could be, let's say, the training throughput for a job if I get X number of GPUs allocated to it. But typically, these markets are static, where you have a time invariant utility. And in our case, to handle dynamism, we actually had to have a time variant utility that we introduce into these markets. So we built this sort of new idea as a volatile Fisher market in Shockwave. And every training job here has a time varying utility, and we solve for an allocation that leads to a market equilibrium. We prove a lot of strong properties about this market equilibrium. We prove that this maximizes cluster-wide utility, where utility is like summed over every round of allocation, and we take a product of all of the jobs to get a cluster-wide utility. And we also prove that this minimizes this provides sharing incentive by minimizing the product of these finish time fairness values across all of the jobs in the cluster. So we put this all together in this system that we built called Shockwave. A quick overview of the system diagram looks something like the jobs arrive or trigger their batch size changes. And we pass those events into this Bayesian predictive model. The Bayesian predictive model comes up with a predicted runtime and predicted batch size for each job. And we use that to estimate the long-term efficiency and fairness and feed that into our social welfare solver, which is based on Gurobi. And the solver produces allocations not just for this round, but also into sort of a fixed window of rounds into the future. We use around 20 rounds always into the future, just for the sake of solving it in a fixed duration of time. So we evaluated Shockwave using a number of different scenarios, both in physical cluster and using simulations. We use workloads from Gavel, which is an OSTI 2020 work, and also from Microsoft PhillyTrace. And we use a mix of GNS and accordion jobs that I described before in this talk. I'm just going to give you a quick high-level overview of the overall results. There are much more detailed results in the paper. Just in terms of end-to-end comparisons between Gavel, which is doing instantaneous fair sharing, and Themis and AlloX, which are using the filter-based approach I described before, we can see makespan improvements of around 1.3x, and the percentage of jobs which have unfair allocations improving by around 2x. The really nice part about this is that we are able to do all this while maintaining the same responsiveness or the same average ACT compared to all these prior works as well. We also did a deep dive into where are these wins coming from. And we can see that Shockwave is able to sort of opportunistically schedule these large jobs during execution across rounds, whereas existing works typically don't have a very accurate estimate. And so you typically have traces where these long jobs are sort of straggling, and you have very low cluster utilization affecting the makespan. And we can also see this sort of in these finish time fairness numbers, which are in the CDF, which is that we are able to sort of have a much shorter tail for the CDF of finish time fairness values. So to conclude, dynamic adaptation of machine learning jobs introduces sort of new challenges in scheduling for both fairness and efficiency. To address these challenges, we built Shockwave, a new predictive scheduler that uses this market-based formulation. Our source code and sort of scripts to reproduce our experiments are available at this GitHub repo, and I'm happy to take any questions you have now. Thank you.